In this video, we're doing example 7.7.6, where we're asked to look at variables x and y that have joint density function here, and then calculate the expected value of y given that x is equal to 2. Two ways. One, from the definition, and two, by noticing that x and y are independent. So let's start by setting up the first. So by the definition, we need to integrate the expected value of y given that x is equal to 2 is, well, the integral from minus infinity to infinity, so over all y values of y times the conditional density function, the density f sub y given x is equal to 2 of y given x is equal to 2 dy. Now, this conditional function we need to find, and so let's write how that is calculated over here on the side. F sub y given x is equal to 2 of y given x is equal to 2. Well, that's the joint density f of xy divided by the marginal f sub x at 2, right? So we know x is equal to 2, so we'd be plugging in 2 into the marginal function. Now that means that we need to find the marginal for x. So f sub x of x is, well, we want to integrate out the y. So the integral from minus infinity to infinity of the joint density function dy. And so let's have a quick look at the support. X goes from 1 to 3 and y goes from 0 to 3. And so we have a nice rectangle here. If x goes from 1 to 3, y goes here. And so we end up by having a support which looks something like this. So from 1 to 3 in the x and from 0 to 3 in the y, which means that we want to integrate from 0 to 3 because we want to get rid of all the y values of 1/6 dy, and you can use a property of integrals, or you can actually integrate that 1/6 y from 0 to 3 and you get 3/6 minus 0, or 1/2. So that's what's going to go in our denominator here. So to find the conditional density function, f sub y given x is equal to 2 of y given x is equal to 2, then this is just the joint density again divided by the marginal density evaluated at x equals 2. Well, both of those are constants, so I'm just doing 1/6 divided by 1/2, which gives me 2/6, or 1/3. And then finally, I can go back to the initial integral, which gives me the expected value. So the expected value of y given x is equal to 2 is that integral, which we'll just recopy. So the integral from minus infinity to infinity of y times the conditional density function, and that takes longer to write than to actually calculate almost. So we're going over all y values again, so we should really have written here that this marginal for x is valid from x is 1 to 3, and this conditional for y, well, if x is equal to 2, then there is no change in the y values that we can have, and so that is from 0 to 3 as well, and that means that we are going to integrate again from 0 to 3 of y times the conditional, and the conditional is sitting right here, so y times 1/3 dy, which means we need the antiderivative y squared over 2, so we're going to get 1/6 y squared from 0 to 3, which gives us 9/6, or 3/2. So there, from the definition, using the integrals and the conditional density function, there's our answer, 3/2. Now we're asked to also notice that x and y are independent. So how are we supposed to notice that? Well, the joint density f of xy, it's a constant, but it can be expressed, any constant can be expressed, as the product of a function of g of x times h of y, where both of these necessarily have to be constants as well. And that is true over a rectangle, over this rectangle up here. And we saw a proposition in a previous video that if the joint density function factors into separate functions of x and y over a rectangle, that is enough to tell us that x and y are independent. And so if x and y are independent, And this function is a constant, so if f of xy is a constant, then we have to have that x and y themselves have constant density functions, which means that they are uniform. So these are uniform. And in particular, if y is a uniform variable over this integral interval from 0 to 3, then we have, so it's uniform from a equals 0 to b equals 3, then we know its density function, so f sub y of y is 1 over b minus a, which is 1 over 3 minus 0, or 1/3. And if we know that x and y are independent, then the expected value of y given that x equals 2, well, given x equals 2 is irrelevant if y does not depend on x. That's just the expected value of y, which, if we know that they are uniform variables, is just from the uniform distribution a plus b divided by 2. That's the expected value. So that's 0 plus 3 divided by 2, or the same 3 over 2.